Are you saying that because he's a sloth, he can't be fast? Flash, flash, 100-yard dash. Buddy, it's nice to see you.
Nice to see you, too.
Officer Judy Hobbs, CPD, how are you?
I am doing
Fine?
well. What
Hang in there.
can I do
Well, I was hoping you could run a play.
for you
Well, I was hoping you
today?
Well, I was hoping you could run a plate for us. We are in a really big hurry.
What's the plate
29 T
number?
29 THD03.
2 9 T
HD03.
H
D03.
D
03.
0.
3.
Hey, Flash, want to hear a joke?
No!
Sure.
Okay. What do you call a three-humped camel?
I don't know.
Pregnant.
All right. Good morning. So today I was like thinking about what's the song I should play, and sometimes like suddenly you feel like, yeah, there's something that I definitely should put here, and it turns out that it reminds me the movie called Zootopia, and there was a scene, and today we are talking about dynamic instruction scheduling, and there is a scene like what you just saw in a DMV of Zootopia. They talk about how slow their operation is, and it turns out that if you have slow hardware, then dynamic instruction video, and if you don't even didn't even have the chance of watching the movie Zootopia, you should definitely do it. And it's one of the best movie that I ever watched. And if you ever live in California, you will feel like, yeah, they like you must have this experience about like spending your time in DMV. But before we talk about that today, we still have to recap on a few things, and then I will talk about how our lecture today is related to Zootopia. So before we start, it's always good to put you guys in a context. Why are we here? And the reason why are we talking about the topic that we are going to talk about today is that we mentioned that although we have pipeline processors, and in theory, pipeline processor can give us one instruction output per day, per cycle. However, there are three pipeline hazards that prevent us to achieve such optimal throughput. And the first type of hazard is called structural hazard, meaning that resource conflicts cannot support the simultaneous execution of instructions in a pipeline. And the second type is control hazard, meaning that, well, the key to pipeline throughput is that we want to be able to keep fetching instructions and keep executing instruction. However, there are cases where we cannot determine what's the right address to fetch. And it turns out that's because you have branch instruction, and that's called control hazard. And the last type of hazard, which is the one that we are going to focusing on today, is the data hazard, meaning that an instruction cannot make progress because it's waiting on the result that has not yet been generated or propagated yet in the pipeline. So previously, we mentioned that if you want to address structural hazard or control hazard stalls, meaning that we just don't stop fetching instructions and then pause the current progress of a few instructions, that would help. And however, as we could all imagine, is that it's just really slow, like what we spend, how we spend our time in DMV. right? But a more effective way is for addressing the structural hazard is that's just modify the hardware design to allow more concurrent accesses. And for control hazard, you can do branch prediction because the issue is that we don't know what to fetch, right? And with prediction, at least it would increase the chance that we fetch the right instructions. So finally, and we spent a lot of time talking about the ways of addressing branch predictions, and we have learned like neural network. We even learned like neural network based predictions, right? But now that's moving into data hazard, which is also a huge amount of a huge part of the hazard that we are interacting with every day. So the reason why we have data hazard is because there are data dependencies, and the data dependency cannot be resolved in a pipeline, and that's why we have data hazard. So if the only approach that you can deal with data hazard is through stalls, then it turns out that every data dependency would become hazard. So today we are going to talk about better ways to address data hazard. So before that, here is the current standing of each group, and we can see Valors are catching up, and Rocket and Instinct, you guys are not too far away. And the two mechanisms that we are going to talk about today is data forwarding, Tomasulo's algorithm. So the solution to that we mentioned instead of stall is data forwarding. So the basic idea of data forwarding is that since we are having hardware issues of propagating. So if you look at the pipeline we have, right? If we stall, then it turns out that everyone has to wait for the instruction write back to receive the value they need. However, if you spend time carefully, you will figure out that for load instruction, we can actually get our value at the memory. The value is actually in a pipeline in the memory stage. It's just because there is no bypass hardware allow us to propagate this value to the instruction. For example, like this instruction. So we have to wait for additional cycle. And same thing here is that for the X7, after the execution stage, we already have the right value for X7. However, because there's no appropriate hardware for us to pass this result to instruction, so we have to stop. So in this way, right, the basic idea of data forwarding is that we just add a few logics and wires to forward the desired values to the demanding instructions. And in our 5-stage pipeline, there are two places that would generate result. The one is the execution stage, and the other one, so the one is as I mentioned is in execution stage, and the other is in the memory stage if the previous instruction is a low store instruction. And now the thing is that if the instruction entering and when do you need this value is when the instruction needs to enter the execution stage. We are going to need these values. And at the time, the instruction that was originally in its execution stage is entering its memory stage. And for the instruction that generates value in its memory stage is already in a write back stage. So the key thing is that if an instruction that is entering the execution stage can find its value in from a previous instruction in the memory stage or the write back stage, and we can potentially forward those values to the LU in the execution stage for the later instruction to continue execution. So that's the basic idea of data forwarding. So you probably never pay attention to this graph. And what I can tell you is this is instruction fetch stage, this is instruction decode stage, this is execution stage, and this is the memory stage, and this is the write back stage. And fortunately, because this is a graduate level course, so I'm not asking you to understand what's going on in detail. But even though even so, there are still things you have to pay attention to, is that how we implement the data forwarding is that, as I said, right, if the instruction is now entering the execution stage, it will needs the value, it may needs the value from the previous LU result. Then we have this logic here. And if sometimes my value is in an instruction that's currently in its write back stage, I get a value from here, right? So that's the whole idea of data forwarding, is that we just have bypass logic to forward the value from wherever we want. So given the idea of data forwarding, and given the assumption that, well, we are able to forward a value that an instruction desires whenever whenever the value is ready in a pipeline. For the previous question, how many stalls or how many data hazards do we still have in the pipeline with full data forwarding, as I just depicted in the previous slide? All right, 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you, there is a tie between B, C, and D is also a popular answer, which means that you guys really want to discuss with your friends. And let me pull out the group. Okay, so now let's start a group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now when we look at this, looks like the result shows like it's still very close in B and C. So we definitely want the whole classroom discussion to see what you guys are thinking after the discussion. So Mystics, we need some of your insights. Hello, our most top. Okay, so I have Ashai.
So our team thinks that the answer should be B.
The
That
answer
is
should be
one.
B, but how come?
Yeah, so there would be only one stall when we have a load instruction and then we have add instruction. So for add, we require x6 to be present, and x6 is not
Mm-hmm.
present till the load, the mem stage of the load.
Right. So
So
when we draw the pipeline diagram, right, do you mind to walk through the pipeline diagram with me?
yeah,
So in the very first cycle, are we able to fetch the load instruction?
so yes, there's first would be instruction
And
fetch.
then how about the second cycle? What happened?
So we will have instruction decode for the load,
Mm-hmm.
and we will
Mm-hmm.
have instruction fetch for the add.
Okay. And how about the
And
next cycle?
so for next cycle, we will have execution stage for load, and we will
Mm-hmm.
have decode for the add, and then we
Mm-hmm.
will have
Are we able to
fetch.
fetch the store?
Uh, y-
Yes, right,
yes,
because
right.
there's no branch, so we can keep fetching, right?
Yes,
So
right.
now how about the next cycle?
So for the next cycle, we will have the memory phase
Mm-hmm.
for the load, and then we have decode for the add, and then we will have
Why the add has to be in decode?
because for the previous decode, we the x6 is still not available, and it is not produced
Okay,
by load instruction.
okay.
And
So
yeah,
then can store go into its decode stage?
uh, no, because
Because if you do that, there will be structural hazard, right?
right.
So then how about the next cycle?
So for the next cycle, we will have the memory cycle for the load. Oh, sorry,
Mm-hmm.
sorry. Let me just. Yeah, right. So
Right.
yeah,
So then in the next cycle, because there's data forwarding, so we could forward the result from the memory stage to the execution stage, right?
right.
And if you keep going for the store instruction, right, there could be a data forwarding from the add instructions outcome to the store's memory inputs, right? And for the add instructions, it would generate the execution. It would generate the x10 value in the execution stage, which is also needed by the branch not equal instruction. So yes, thanks Aishai, and thanks for the insights from Team Mystics. So the truth is that if you have full data forwarding, there's only one pair of instruction would cause the store. That's the load and add instruction, right? Because for arithmetic instruction, we can always generate the value, the outcome in the execution stage, and you can always forward your outcome to the execution stage of your next. If there is an immediate instruction using that result, you can follow up with that. However, for load instruction, you are generating your result in the memory stage, and that's why you cannot do that. So there's only one group of them needs to that will cause stall. That's actually the load and add instruction. So that's why for this question there's so with data forwarding you can see previously with only stalls, then every instruction with data dependency would cause, in this example, would cause a data hazard. Now with data forwarding, only one cause hazard. So, and because that's the only case that would cause data hazard. So you want to make the data forwarding, if you want to make the data forwarding pipeline working perfectly, you need a hazard detection unit here to detect if there is a case of a loaded instructions producing the value of an immediate arithmetic instruction that would compute, that would be consumed by the later instruction. That's the only case we need to store. So that's why we have the hazard detection unit in addition to the data forwarding logic in a complete pipeline design. So now, so it sounds like data forwarding would resolve our issue. However, think about this, right? If our pipeline gets deeper, right? Saying that if I have a newly designed pipeline with memory stage that has been split into 2 stages. So saying that, well, like because the processor memory gap problem, right? So your processor and memory speed, they are deviating. So you definitely, and to keep the processor speed scaling, you definitely have to partition your pipeline into more stages in some cases. So saying that if I have a pipeline, right, then what will happen is that you will see that if your pipeline stage is getting deeper, then the data forwarding, it does help. However, you are going to increase your stalls, right? So that's not a so data forwarding is also not a perfect solution in a way that if your pipeline gets deeper and deeper, right? The case is that the instruction that would get stalled or the number of stalls you have to experience is also increasing with your pipeline stages. So your overall your pipeline performance will not be great, right? So in this, and the other thing is that if you look at for other, that's not the only issue. If you look at other instructions like this add instruction, like those arithmetic instructions or branch not equal instruction, those additional stages that we added to accommodate the longer memory access time doesn't make any progress for those instructions. So this is not actually a very perfect solution, right? So another way that we can think about, and another thing that people would think about that, well, we can potentially address the data hazard issues if we have a better compiler. So now I'm asking you, okay, you assume that you have a smart compiler, and this is exactly the code that we have shown you previously. What can you do? All right, let's wrap up in 15 seconds. Oops. Five, four, three, two, one. Time is up. Okay, so after discussion, well, we still see a pretty evenly distribution among you guys. So why don't we just have a group discussion real quick? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now after discussion, I see more of you think it's E. So I want to invite some of the group sharing your thoughts. Why do most of you change your mind? Okay, Rocket Tim. I feel like the next time maybe I should play a music for Rocket Team. Okay, Winston, you are not Rocket Team, I remember.
Can I get points for my team?
Okay, so first of all, is there anyone from Rocket Team want to raise your hand? Okay, maybe not. Okay, Winston, go ahead.
Our group, so some of us thought that you couldn't, none of the pairs could be reordered because of possible hazards. Like I thought you could switch 2 and 3. So I was entirely
2 and
sure.
3, but why do you think 2 and 3 would work?
Switching them? I thought that if you switch 2 and 3, I might be wrong here, but I think it would delay the issue here that we're having is the mem is happening a little bit too early. So if we delay the add cycle by one, the mem and the ID should line up. The instruction decode stage and the mem stage should line up for the load. And
okay, so let's say, right? So saying that this is the store instruction and this is the add instructions, right? And the add instruction would go is in, well, so first of all, right, the store instruction would be in if, id, exe, mem, right? And write back, right? And the add instruction would be instruction fetch, decode, execution, mem, write back, right? And the store instruction would need the value of x7 definitely in the beginning of me, right? And the add can only generate the right value of exe at the end of exe. Will that work? Will that work? It doesn't help, right? And if you really want to make this work, and if you are aware they have the dependency that you really need the value of x7 to be here, it turns out that the store instruction here will incur more stall to make it work, right? So this is definitely even worse if you do that.
Yeah, okay. That's what I thought, but most of everyone else in my group thought you couldn't do that because of the that I think that dependency actually, yeah.
Right. So the answer is that, well, some of you might think that the compiler can do a lot of things for you, but the thing is that a compiler cannot do anything here, right? But it's great to hear like why in the very beginning you guys were thinking about, yeah, why this, why, well, some of you, so before there were other answers, right? But now we can see like, oh yeah, so the reason why 2 and 3 cannot be reordered is because it just doesn't work out. Right, so you might think there are chances for code optimization. Actually, this is already the perfect sequence of the code that you can compile, and we still stalls, right? So now another thing is that, okay, if we say that we can back to the future, or say if we can predict the future, and given that we have neural network predictors, right? If you can predict the future and assume that the branch prediction is perfect, that that instruction from 6 to 10, they will be executed for sure. Is there a chance that we can have the compiler work out? Or say the code reordering work out? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this time, I see the answer is pretty consistent within groups. So well, within most of you, but I still want to make sure that you guys know what you are thinking about. So why don't we just have a quick discussion, so hopefully we can finish the whole thing within 2 minutes. Go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now after discussion, wow, we have seen 75% of you think is C. So now I am going to invite a group to share your thoughts with us. However, when you tell me your thoughts, not just sharing why you guys think C is correct, but also why others are not correct. Okay, Tim, you guys got good luck for today. Who is your scriber of the day? Can you raise your hand? We need you. We want you. We need you. Hello, somebody there? Somebody there? Okay, I have Daniel. Wait, Daniel, you are team.
I am not on Rocket, but I'd like
yeah,
to.
I remember
snatch
you are
this
Valors,
if
right?
possible.
But okay, since no one in Rocket would speak up, so what do you guys think? You finally got your microphone today. Hello?
I can't hear it.
Are you there? I can hear you. I can hear you.
Yeah, so I'm not
Hello?
on Rocket. I'm not on Rocket.
Yeah, I know. I know you are not on Rocket.
Oh, okay. Can I answer or no?
Sure.
Okay. So we chose C for well, I guess I can start with the reasons why we can't choose A, B first.
Okay.
So for A, when you swap 2 and 3, or 2 and 4, it's moving the add instruction after where it's needed to store in 3.
Mm-hmm.
So
the store cannot get the right value.
yeah.
Right.
And then
okay.
So when you swap 3 and 5, 3 and 5, you move the branch instruction in front of the add, and you need the add immediate for the branch instruction. So that doesn't work either. And then 5 and 6 works because there's a stall between add
Well,
I.
so for 3 and 5, right? Oh, yeah. Okay. So for 5 and 6.
Yeah, so for 5 and 6, you can move the load in front of it, and that does not affect the correctness of the program at all. And then,
Right. If the branch is perfect.
yeah,
Right? Branch prediction is perfect. Okay.
and then 6 and 9, let's see, 6 and 9. You need the X6, excuse me, for the add instruction. So that's not going to work. And then 9 and 10, you need the add I instruction for the branch instruction. So
right. So you cannot, the only choice you can make here is actually 5 and 6. And thanks, Daniel and Team Valor. Okay. So Rocket Team, you missed 2 chances today. So please, right? So so now the thing is that, okay, we identified something, right? So there is limited capability for the compiler to reorder the instructions. And another thing is that if we have branch prediction and the branch prediction is perfect or nearly perfect, or there is a way to revert the incorrect prediction result, we can potentially reorder instructions without affecting performance, but improving performance, right? Without affecting the correctness, but improving the performance, right? So, however, who does the branch prediction, right? The compiler has no way to do branch prediction. Compiler has no way to revert, even though the compiler has some kind of software can do branch prediction. Let's say, assume that would happen, but there's no way for the compiler to revert incorrectly generated hardware result, right? So turns out that, right, we need the hardware's branch prediction to predict the future, and the ability to reorder instruction across the branch to optimize our performance. So here comes the idea of dynamic instruction scheduling, or say out of order execution. So so it comes from, so how do we achieve the out of order execution? So let's go back to the tips of drawing a pipeline diagram. So we say that when we are ready to draw a pipeline diagram, if we can execute an instruction or not, or if an instruction can make further progress or not, is simply depending on these 3 policies. First of all, no other instruction is occupying the next stage, or say the target functional units that I am looking into. And the instruction has done its own work at the current stage. For example, it has finished decoding, it has finished fetching, and the next stage has all its input ready. So if I am going to execute this instruction, then it turns out that I need all the inputs to be ready for the instruction to enter the execution stage. So here are 3 top guidelines that we can execute an instruction or not. But there is nothing talking about if the instruction has to be in order. So here we come to the idea of out of order execution in a way that we are designing a hardware that can execute an instruction, or say put an instruction in the execution stage whenever an instruction is decoded, meaning that the job needs to be done in the decode stage is already done. And whenever all the inputs are ready, means that all the data dependencies that are associated with this upcoming instructions are resolved, and whenever the target functional unit is available. So if we have this three things, then we are ready to execute an instruction. So that's our policies in designing, or say that's what we are going to do, and we are going to design a hardware that allow us to do that when in a processor. So here's the thing, right? If you can do that, you are actually scheduling the instructions based on your data dependency. Because if you look at the previous one, right? Whenever your instruction is decoded, whenever the target functional units is ready, and whenever your inputs are ready. So as long if you have unlimited, if you have all instructions decoded, if you have unlimited functional units, in the optimal dynamic scheduling is just basing on your data dependency graph. So it's really important that if you want to analyze the potential of dynamic scheduling, you have to figure out if there is a data dependency or not. So that's why we have the question in the last lecture, we're asking about data dependency. So if we want to use the graphical representation for data dependency, we will create a data dependency graph, which we will create a single direction acyclic graph that we put an arrow from an instruction to another instruction if another instruction is depending on the output of an instruction. So saying that we have 10 instructions here, right? For instruction 1, it generates the output for instruction 2. So we have an arrow here. And for instruction 2, it generates the output for instruction 3. So we have an arrow here. For instruction 4, it does not depend on anything from 1, 2, 3. Instead, it generates the output for 4 and for 5. So 4 and 5, they have an arrow. And for 6 and 7, they are depending on the so for 6 it depends on the output of 4, and for 7 it depends on the output of 6, and for 8 it depends on the output of 7, and again for 9 it depends on the output of 4, and for 10 it depends on the output of 10. So if you look at this data flow graph, you will figure out that instruction 1, 2, 3, and the instruction sequence starting from 4, they are from a completely different sequence. And they don't have the actual data dependency involved. And in theory, we should be able to execute these two parts in parallel without affecting the correctness, right? However, is it that easy? Is it that easy, right? So now I'm asking you, right? Given this is the data flow graph, are we able to execute? Oops, I forgot to put my timer here. Okay, are we able to reorder any of this? Wait. If the branch prediction is perfect. Okay, so no, this is exactly the same question we had before, right? So if you remember this question, right? Like we said that we can so this is exactly the code we have before. But if you look at that, right, given the current pipeline, right, given we have the data flow graph, right, if you compare the data flow graph, you will figure out that, well, although we said that 1, 2, 3, they are completely independent from 4, 5, 6, 4 to 10. And in theory, we should be able to mingle all the execution of the instruction sequence from 1, 2, 3 with any instruction from 4 to 10 to minimize the overhead, to minimize the stalls or whatever, right? But it turns out that even though 2 and 4, they are not depending on each other at all, we are still having issues of reordering them. And why is that, right? Why is that? The reason is because we are still limited by false dependencies. So the reason why it's called false dependency is that because you won't see them in the data flow graph. So that's why they are called false dependencies. They are not true dependencies. So, well, some of the people, you are really great that you start to look ahead those materials. And at the end of the last lecture, after the end of the last lecture, I received a few emails asking about why these are not data dependencies, because they are so-called false dependency. There's a politically incorrect analogy I want to give you here is that, like a lot of us has been done with the COVID-19 test, and some of you, I don't know if any of you, but some of the positive cases turns out to be false positive. Right. So if someone is claimed finally we figure out it's a false positive case, does that person really have COVID-19? The answer is no. So here the same for false dependencies. If they are not true dependencies, otherwise we won't put false in front of dependency here. So the reason why they are not true dependency is because they are not really depending on the output of the other. However, they would, if you, because there is something else in our hardware that limits the capability of reordering them. So if we reorder this sequence of instruction casually, that would cause the incorrect result. So if you execute them in sequence, then there is no dependence, there is no issues, and there is no incorrectness. However, if you try to reorder the sequence, then it will cause issues, and that's what we call by false dependency. So there are two big categories of false dependency. The first one is write after read. Or say war. It's a later instruction overrides the source of an earlier instruction. So, and in microprocessor, we usually put our source values in registers. So it's the case that a later instruction try to override the result in a register that an earlier instruction is still working on it. So in this way, if you try to reschedule that instruction, to rewrite that in the register earlier, it will cause the result that other instructions are still depending on to vanish. And that's how you get the incorrect result. So in this way, we found like, okay, the big issue here is that for instruction 1 and 4, although they do not have the data dependency, like the instructions 4's X10 is not coming from any of the instruction from 1 and 3. However, instruction 1, depending on an earlier X10 that will be later overridden by instruction 4. So if you don't finish your instruction decode stage for 1, 2, 3 before the 4th instruction overriding the X10 value, there will be incorrectness for your code. So that's why 4 and 1, 4 and 3, there will be a write after read data dependency. And similarly, you can imagine for instruction 9, there will be 9 and 5, 9 and 6, 9 and 8. They all fall into the same category. And for instruction 6 and 2, if you try to load twice, then this add is not going to get the right result. And similarly, for instruction 7 and 3, if you try to add twice before the store, then the X7 will not getting the right value. So the key thing here is that because the sharing of registers, so the write after read would cause an issue. And another case for that is write after write. So a later instruction overrides the output of an early one. So for instruction like 6 and 1, if I try to load the value twice here, then it turns out that the one of the X6 is going to be vanished, and the later instruction won't be able to get the correct result. And for instruction 7 and 2, if I try to have two of them executing together, or one of reorder in such a way, then it turns out that the X7 would be missing for some of the instruction that depends on the value. So for these cases, if you don't change the instruction order, there will be not issues. There won't be any issues. So there is not really a data dependency. But what really causes data dependency is your intention to change their order. And the reason why when you change their orders and it won't work out is because we have limited registers, because they are sharing the same registers. So these are the cases that where we see those false dependency gets played in, right? So now, now I want you to identify for this following code sequence, which of the following pair of instructions is not a false dependency, to see if you really understand or get the idea of false dependencies. All right, let's wrap up in 15 seconds. Oops. Oops. All right, 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, well, this result seems no, the distributions, right? So now, why don't we just go ahead and have a group discussion real quick and see if that helps. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, we see a majority of you think it's C right now. So I want to invite a group talking about why C is the answer. Okay, Valor. Somebody there, somebody there. Somebody there, somebody home? Okay, Daniel.
Hi. So
Yes.
the reason why it's not a false dependency is because it's read after write, which is a true dependency, because you're writing the result of the addition between x18 and x12 into x14, and then using
Right.
and then
So if
storing
you
that.
want to figure out if, yeah, okay, sorry. Okay, so for the first option, what type of dependency is it?
For 1 and 4, it's going to be a write after write because you're loading into
Right,
x12.
because we are overwriting 12, right?
Yeah.
How
And then
about
for-
1 and 8?
For 1 and 8, you're loading into x12 and then 8. Sorry, let me see. Oh, that's a read after or write after read, because
Right, and for C, as you mentioned, right, it's a true dependency. For 4 and 8, how about them?
4 and 8, it's a write after read as well.
Oh, 7 and 8.
And 7 and 8 is again write after read.
Right. So perfect. So for this, to identify who are false dependencies, who are true dependency, well, the easiest way is that, well, you can see, like, for true dependency, it does has an error between 5 and 7, so it's a true dependency. And for others, you don't see an error right there. So if they have some issues of reordering them, they must be false dependency. Okay, thanks Daniel and Tim Valler's group, the answer, right? So the answer will be C for this question. So now the issue is that if we want to do out of order execution, but turns out that we are still limited by false dependencies, and there are very limited chances that we can make out of order execution work. So how can we design a hardware that extract as much parallelism as possible and without being restricted by the false dependency? So here there's a computer. This is really a computer. It's called IBM. It was working in one of the museums, right? And it's actually the first. It actually demonstrates one of the very first out of order execution algorithm called Tomasulo's algorithm. And this machine is called IBM 360 Model 91, and it's the most powerful commercialized machine in 1968. And I guess most of us were not born at that time, including myself. And this is the first machine with out of order execution. So that Tomasulo algorithm was implemented in IBM 360. And but before Tomasulo algorithm, there is CD6 6600. They have out of order execution using scoreboarding. And the scoreboarding is another dynamic scheduling algorithm that currently not in the main text of the textbook, but it was one of the very significant one in the past. And But because the textbook is not emphasizing scoreboarding anymore, so I just want to let you know, in addition to Tomasulo, in that very old time, there is another algorithm called scoreboarding. And the basic idea of scoreboarding is that there is instruction storage attached to each functional unit. So each functional unit has its own instruction queue, and instruction will be able to issue to functional units if the structural hazard is resolved, and the execution begin execution when dependencies are satisfied. So and instructions that belong to different functional units can execute out of order. And so that's the basic idea of scoreboarding. But they have a distributed instruction storage for each functional units. And now, what is Tomasulo algorithm? So Tomasulo algorithm is another way that's similar to scoreboarding, try to get rid of those false dependencies when we are executing hardware. So if you look at the pipeline stages that I draw below, in addition to the instruction fetch, decode, and the write back stage, we modify the standard part of your processor pipeline. We add a few stages here. So first of all, we have a dispatch stage. The dispatch stage meaning that we are allocating a reservation station for the decoded instructions. So what is a reservation station? So at this point, I want to, maybe I could, what I can say about reservation station is a storage of value. And so we mentioned that previously we have issues with false dependencies because instructions, they share the same register name. So reservation station is a temporary buffer for the instruction outcome. So if you want your instruction to execute, and you definitely want a buffer for your outcome that is guaranteed to make sure that your value is not vanished during the execution. So that's the meaning of reservation station. And there is another stage of issue. It's meaning it's a stage that, okay, we got a reservation station, but remember, what we need to execute an instruction is to make sure that all inputs are ready. So this is the stage where we are collecting all the pending values, branch outcomes from a common data bus. So the common data bus is a broadcasting network to tell all the instructions in the reservation stations, or say all the instruction that's in the issue stage, if you are ready to go. And in the execution stage, we mentioned that the previous pipeline would have the waste issue of shorter instruction has to waste its time in longer because of the longer instruction. So we decouple the pipeline of the execution stage for different instructions. So now for the branch instruction, it just has one stage. For integer instruction, it just has one stage. For the memory instruction, we have three stages: the address queue, the address resolution, and the the real memory access. And for this M1, M2, M3, they are for multiplications. So this is the Tomasulo pipeline, what the Tomasulo pipeline looks like. And when your instruction finishes, we will broadcast the result through CDB to activate an instruction. So the write back state and the CDB, as we mentioned, is the common data bus that everyone will hear, and everyone who has the value ready would be able to execute. So if you have ever been to DMV, right, this is like whenever you are waiting. So when you are sitting, well, so first of all, right, when you enter the DMV, right, it's like instruction fetch, and then you go to the counter of DMV. Someone is trying to figure out what you want to do, what business you want to do. So that's called instruction decode stage. And then they will give you a number like B B16, right? Then that's the dispatch stage. And then the issue stage is whenever you sit inside the DMV. And when DMV, those staffs are serving other people, they are executing. And when they are done with one people, they will press a button, and then you will hear from the hall saying that now serving B16 at window number 27. Right, so that's like the right backstage and the common data bus. And so you will feel like, so now you know why I pull up that Zootopia video here, because this Tomasulo algorithm is exactly like what we do in the DMV. And in theory, that should be really efficient. However, when we put into practice, is not like that way when we have it in service in DMV. So, but assuming that in the good old times, it was one of the best algorithm in scheduling for processor instructions. So here's the overview how we implement that in hardware. So first of all, we still have the first fetch decode instruction, and for those instruction that has been fetched decode, we put them in the instruction queue. And then there is a register status table to tell you if I want to find the value of, say, like register X1, which reservation station would give me the right value of it, and or say what's the current value of that, right? And then I have a few reservation stations that are associated with each functional units. So each reservation station would contain what's the target. So for example, for address queue, because it's associated with low store instruction, so it will further tell you like what's the reservation station number for the low store instruction, what's the immediate field, what's the address, what's the address operation, and if it's a for integer instruction, it also tells you what kind of instruction it is, what's the operand one, what's the operand two, right? And same thing for other instruction like add or mul. We have this add here is the floating point add, and for this mul, it's the floating point mul, right? So they all have the same thing, right? And the SDB means that if this instruction is speculative or not, right? So this speculative means that the branch is not resolved yet, right? So so with that, right? So then we will connect this reservation stations to the corresponding functional units, and whenever the functional units is free, we would issue an instruction from the reservation station to the integer to the corresponding ALU. And for low store instruction, as I said, there are further stages of reservation stations storing the putting the value of load in store. And then once you are done, the result will be broadcast to common data bus, and they will update the register status table and notify the reservation stations. So that's the overall hardware for Tomasulo algorithm. So let's have a walkthrough of Tomasulo algorithm for this pieces of a code that we just seen. So in the very beginning, we still assume that all the instructions are currently fetched and decoded. And now in a pipeline, we can only decode, dispatch one instruction at a time, right? So in the first cycle, the load instruction has a because now all the reservation stations are empty. So we can definitely find a reservation station for the load instruction. And then in the next cycle, the load instruction has no issues being issued. So we put them in the address queue. And for the add instruction is now being decoded, dispatched. And by dispatch, we mean that it means that we are going to give it a reservation station. So the second cycle, we can do it. And the third cycle, the load instruction can go into address resolution, and for the add instruction, it has to wait to issue. And for the store instruction, again, it's in its dispatch stage, and we still have a reservation station for the store, so that's fine. And then in the next cycle, the load instruction down is with its address resolution, but we have to wait for an issue because we are not sure if because we have to check if the target functional units, which is your memory state, which is your memory, if that's ready. And for the add instruction, it still has to wait in the issue stage, because if you look at the add instruction, it has to wait for the not only the input for X12, it also have to wait for the input from load 1 reservation station. And the load 1 reservation station is currently not resolved yet. So we cannot issue add instruction at this moment. And now let's keep going the next cycle, because currently no one is on the memory stage. So the load instruction can keep loading. And for the add instruction, because it has to wait for the load instruction to finish, so it still has to wait for to stay in its issue stage. And for store instruction, it can keep calculating its address. And for the add immediate instruction here, it's now finishing its dispatching stage, because we have a second reservation station available for add instruction, and the issue stage right now is just waiting to check if all the inputs are available at this moment. And if you look at the right now, right, this X10 value, we don't depend on others' X10 value, right? And the X10 value of 1 and 3 are already recorded in the reservation station. So we don't need those values in fact. And for this X10, the additional X10 values that we are generated, it will be put into add 2, right? So we are not actually overwrite. So we have a place to find the generated X10 values, and all the follow-up instructions that depends on the outcome of 4 will be using the add 2 reservation stations, like this store instruction is now its source is coming from add 1 as well, right? So so like the later branch instruction, right, we will rewrite its input as add 2 instead of X10. So the value is not missing at all, right? So in this way, you will see, even though in the next cycle, right, the add I instruction is executed ahead of add, we are still having the capability of tracking the value of add 2, because the value is now in the reservation station instead of its original instead of in the original registers, right? So that's why Tomasulo algorithm will work in this way, with the idea of reservation stations as the temporary buffer of your output. Now, let's keep going. So here we see the add immediate is now ahead of add. And in the meantime, the load instruction finally write back its results. So you can imagine for the next cycle, right, the add instruction can finally be executed. And at this moment, we want to execute the add instruction. However, we don't have reservation stations anymore, because there are only 2 for the add and add I. So this instruction cannot be dispatched, and we have to have an additional stall here. So that's the limitation of Tomasulo algorithm, is that if you don't have sufficient amount of reservation station, you might still have the stall, and it's this kind of stall is because of the structural hazard in Tomasulo algorithm. And if you keep going, you will figure out that for the sequence of this instruction, it takes a total of 13 cycles to issue all the instructions, with some of them can be out of order to minimize the overall overhead. All right, I know this is a little bit complex, so we are going to walk through this example again in the beginning of the next lecture. And before you leave the classroom, there are still things that I'd like to let you know. So project is off. Check the website, and there is no extension for the project because we are really short on time. Again, assignment 4 is off, start early. I still have office hour this week, and the TA's office hour is very likely to be canceled because Friday is a holiday. And regarding projected grades, again, right, it's the weighted total on iLearn, and it's not a final grading. Don't be sad about that. And that's the whole thing. And some of you were asking me about the final exam logistics in the very beginning of the lecture. So we currently put December 15th as the date, but that's actually the campus day. So my plan is that we are going to finish our final on that day, but I might start the final exam right after our last lecture, so give you more flexibility on the time of working on it. However, regarding the format, I am still undecided because it could be, again, a lot of questions, but limited amount of time, or I will give you a lot of difficult questions, or well, I shouldn't say difficult, a lot of open-ended questions and give you a whole week to work on. I'm still undecided about that. So give me some time to think through that. Other than that, enjoy the rest of your day. I will see you again on Wednesday.